here's another example of projectile motion. We've got a golf ball hit with a particular speed at a particular angle from a tee to a green that is elevated 45 feet above the tee. So assuming that the pin 369 feet downrange does not get in the way, where will the ball land in relation to the pin? So we've got basically a projectile motion problem. There's a tee down here on the level, and then at some point it goes up by 45 feet, and then there's the pin here. So we're going to hit the golf ball at 45 degrees, and it's going to fly up here, and we're just wondering where will it hit the green in relation to the pin. So to set up this problem, we'll remember that the acceleration is 0 minus g. We integrate that function twice, and the first time we integrate with velocity, so we get constants that involve the initial velocity in the x direction and initial velocity in the y directions, and then we integrate again and we get position, and we get these two constants that involve the initial x value and the initial y value. Now what we could do is we could set things up in relation to the pin. That might be a good idea because it wants to know where will the ball land in relation to the pin. So that might be the way to do it. Maybe let's set things up here so that the pin is at the location 0, 0. That would mean that your initial x location is x naught is minus 369 feet, right? So x naught is back over here. And your y naught, since this is 45 feet below where the pin is, then your y naught is negative 45. So we got x naught and y naught. Let's see, we need to find our initial velocity. But if you hit it at 45 degrees, so if this angle is 45 degrees and you've got a speed of 116, then since the cosine and sine of 45, both of those are root 2 over 2, we're going to get 116 times root 2 over 2 for both the initial velocity in the x direction, the initial velocity in the y direction. Let's see, half of 100 is 50, and half of 16 is 8, so that's 58 root 2 in this case. So now we know that v naught x is equal to 58 root 2, and the initial velocity in the y direction, v sub 0 y, is also equal to 58 root 2. Now with that, we can actually we know everything that we need for our position equation. Because we're doing this in feet and seconds, then g is going to be negative 32. So, well, or g will be 32 since we set it up with a negative g. So g is 32 feet per second squared in this problem. Okay, so let's let's actually start working this problem here. I'll kind of shrink this down, and we can write our position equation again. So the position equation is the initial velocity in the x direction, 58 root 2 times t, plus the initial x naught, which is minus 369. And then we have minus 32 over 2 would be negative 16. So negative 16 t squared, plus the initial velocity in the y direction, which is 58 root 2 times t, plus the initial y position, which is minus 45. Okay, so we need to know where will the ball land in relation to the pin. So when it lands, we know that the y value will be equal to 0. So to find when it lands, so when does it land? Well, when the y value is equal to 0. So when y, which is negative 16 t squared plus 58 root 2t minus 45, when that turns out to be equal to 0. Now that's a quadratic equation, and so there will be two solutions. And we know that we need to pick the one, remembering our picture, we can see that it's going to reach the 0 level, right, probably at some time, and then again at a second later time. So there's going to be 2 times when it's on the 0 level, and we want the later one. That's when we're going to land. And then to figure out what our position is when we land, we'll put that back into this formula. Okay, so what we can do to figure out when we land is to use the quadratic formula. Remember, the quadratic formula says that in order to solve at squared plus bt plus c equals 0, you just take this, you do negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's what we're going to use to find the time when we land. Now, in this case, let's see, negative b would be negative 58 times the square root of 2 plus or minus the square root of 58 root 2 squared. I'll pull my calculator here. That is 6,728 minus 4 times negative 16 times negative 45. So that is 2880 all over 2a. Let's see, a is negative 16, so 2a would be negative 32. Figure out what's underneath that square root, and that's 3848. So we have negative 58 root 2 plus or minus the square root of positive 3848 all over negative 32. If I multiply top and bottom by a negative, that might help. So we have positive 58 root 2 minus plus or minus the square root of 3848 all over positive 32. That's nice because now I can see which of these is the one that's bigger, right? If you take 58 root 2 plus this square root, that's going to be the later time. So if you use the plus sign, that actually gives us the later time. So I'll call it T sub L, the landing time, is 58 root 2 plus the square root of 3848 all over 32. Okay, now what we need to figure out is what is the x value at that time. So we know that we're landing, we're on the 0 level for the second time, so that's where we must be hitting the green. Now we want to know what's our x position relative to the pin. We had set the pin here at 0, 0 when we set things up. So we just need to take that time and plug it in here to figure out our x location. When we plug this in for t to get the x value, we get 58 root 2 times 58 root 2 plus the square root of 3848 all over 32 minus 369. I plug that all into my calculator and I get positive 0.254913. So about what, a quarter of a foot. Since this number is positive and 0, 0 was set up here at the pin, this is a quarter foot past the pin. Okay, so remember our steps were that we were going to, we figured out when is the ball on the level of the green, and we used the quadratic formula to solve that equation, and then we found the time when we were on the level of the green. We took the larger of the times, because the first time we would be going up past the level of the green and then falling back down onto the green. So this is where we'd actually have to land, assuming that the green didn't get in our way, right? So this is where this is when we'd have to land, and then to figure out where we had to land, we put that time in to figure out our distance, and it turned out that we actually landed a quarter of a foot past the pin, so it was a pretty good shot.